Hi, everybody, and thanks for giving me the opportunity to present our work here. I am Hyoyin Gan from Kaptein Astronomical Institute in Groningen, the Netherlands. And today I am going to talk about sources of excess noise in detecting the 21 centimeter signal with the LOFAR instrument. So previously, Bharat has introduced a lot of observation techniques. So here I will skip the background and I will directly go into the challenges we face in LOFAR EOR project. And as other speakers mentioned earlier, that the problem of observing the 21 centimeter signal is that the observed data does not only have the 21 centimeter signal that we would like to observe, but on top of that, we have astrophysical foregrounds, which are 3 to 5 orders of magnitude stronger than the EOR signal. But also we have ionospheric effects, which impact the power and the phase of the signal. And further, the signal is distorted by instrumental effects. And also there's radio frequency interference when we observe the signal. So there are some human activities which actually use the same frequency bands that we are using for observing our data. So to be able to extract the 21 centimeter signal from the combination of these different components is very difficult. And the solution is to calibrate the data. So we have to understand those non-signal effects, and then we have to model them. And we finally want to calibrate those things. So remove them from our data accurately. So we have developed a pipeline for doing this calibration job in LOFAR EOR project. And of course, after we have run the pipeline, we would like to know how well we have done the job. And there are many ways of measure the quality of the calibration. And one way of doing it in LOFAR EOR is to look at the ratio between the residual and the estimated noise in the 21 centimeter power spectrum. So here we have one plot which presents the ratio of the residual and the estimated noise. And I took this one from our latest upper limit paper, which is published last year by Mertens et al. And ideally, if the calibration did a good job, the ratio between the residual and the estimated noise should be close to 1. However, in reality, as you can see from this plot, that the ratio is higher than 1. And especially in the foreground wedges, where K parallel is smaller than 0.4, we actually see higher ratio here. So it could even reach 7. And yeah, this is very high. And this extra noise above the estimated thermal noise is known as the excess variance in LOFAR EOR. So before we even talk about detecting any kind of signal, it is important to first understand this excess variance. And then we want to identify where actually it comes from. And further in the future, we would like to, of course, reduce this excess variance. So here in this work, we focus on finding the possible sources of the excess variance. So of course, we know that the calibration is not perfect, and there are some errors in that. And there are some candidates that we think probably the reasons for the excess variance. And this could be some residual foregrounds that we did not completely remove during the calibration. And this could be the sky model that we are using is not complete. And it could also be that the rapidly varying ionospheric effects that we did not take into account when we calibrate the data. And also there could also be some alpha that we did not flag properly when we are processing the data. So here we want to identify those sources and how much they contribute to the excess variance by looking at the correlations. And we focus mainly on the first two candidates, the sky effect and the ionospheric effect. So here I'm going to show some results that we have. So first of all, we have the correlation plots for the excess variance and local site real time. So here, what we wanted to see was the correlation between the excess variance and the sky model. However, it is kind of difficult to directly look at the correlation between the sky model and the excess variance. For this reason, we choose local site real time as a parameter to indirectly look at the correlation. We know that if you fix local site real time, that means that, given local site real time, that the instrument is always seeing the same part of the sky. So you kind of fix your sky model for this specific time slice. And we took 13 nights of observation from our LOFAR data. And then we slice each observation into 3-hour LST slice. And for each slice and each observation, we estimated one power spectrum. And then
Yes.
we average, thanks. We average over K, and we plot the excess variance as a function of local site real time. And it was interesting that we actually see a clear LSD dependency here. So for all the observation we have considered here, they always show the lowest excess variance in LST 3 to 6. So with this, we conclude that the excess variance is correlated to local site real time, and probably for this reason also to the sky model. And to further, if this is true or not, we simulate visibilities based on the sky model. And we do the same exercise. And interestingly, in the simulated Stokes eye power, we see a very similar LST dependence. And with this, we conclude that the excess variance is actually related to the sky model. And then additionally, we also looked at the correlation between the excess variance and the ionosphere. And then here we took the diffractive scale as a measure for the ionosphere quality. So there is so this by definition is the length scale where the phase variance is one squared radius. So what you have to remember is that higher diffractive scale means better ionosphere quality. However, when you look at the plot, you see that for a given excess variance, for example, here around 2, you can have a low value of diffractive scale, can also have a higher value as well. So it's pretty much randomly distributed. And then we see that there's no strong correlation, which was kind of surprise to us. So it seems like that the excess variance is more likely to correlate with the sky-related effects, such as the sky model, than the ionosphere. And in the future, we would like to, of course, combine more data. And so far, we have done analysis pretty much by hand manually plotting A against B. And in the future, we would like to add more data in and apply some machine learning techniques to find correlations more quickly and automatically. So that's about it, and thank you for your attention.